Welcome to the Microscopists, a bite-sized bio podcast, hosted by Peter O Toole, sponsored by Zeiss Microscopy. Today on the Microscopists.
Today on the Microscopists, I'm joined by Chiu, Professor of Bioengineering and Microbiology and Immunology at Stanford University. And we discuss his groundbreaking work in cryo-EM and his future research goals.
So my ambition is somewhat modest but practical, in the sense that I want to understand the organelle in the cell.
Yeah.
Okay. Now every cell biology thought they know organelle because that's what the textbooks teach them, but I don't think we really do.
We discuss his awesome approach to mentoring students.
I think the fun thing being a professor to have an opportunity to interact with the students, I think that's the funnest part of the job. Because I feel the important thing is to learn from the student through their questions. That will inspire my way of thinking.
We also delve into the potential future of microscopy in this field.
That is the current state of art, but there are many yet to be developed technology that I would say 5 years from now, some of these pictures will be replaced by another pictures. Bigger, more expensive, most likely, maybe even taller.
All in this episode of The Microscopists. Hi, welcome to The Microscopists. I'm Peter O Toole from the University of York, and today I'm joined by Chiu from Stanford. How are you today?
Very well, indeed. Thank you. Good morning.
Yeah, good morning, good afternoon, good evening.
Good afternoon, yeah.
Thank you for joining me today on this. I've got to say, I've seen you talk not that long ago, actually, but I was also strongly encouraged to talk to you on a more personal note from the likes of Lucy Collinson, who are big fans of your own. Where to start? Actually, I'm going to ask, what was your first degree? You're known for your structural biology, your biological studies with electron microscopy. But what was your degree in to start with?
Okay, my first degree is in physics. And then at that time, when I finished my first degree, I was thinking, what do I do in the rest of my life? And in those days, I was only pursuing what would be exciting to do. I wasn't thinking about money or position. I'm just thinking, what's the next thing exciting to do? And that was during the Vietnam War era. So students at that era start questioning the relevance of their studies or whatever they're doing. So I thought maybe I want to solve the cancer problem. So that was my really naive way of thinking. And that's why I said, okay, then what do I do if I want to solve the cancer? Since I'm not a biologist, so maybe something I call biophysics. And then that's what I get into biophysics as a graduate student.
So my PhD was also in biophysics, and there's a big difference between physics and biophysics. So that's a huge jump between the two. How did you find that transition?
Okay, so it's interesting because turn out most of the faculty in biophysics at University of California, where I attended graduate school, were physicists once upon a time. And so as a result, their emphasis was always in the physics principle in solving biology. So they place more emphasis on the physics aspect of the biophysics than the biology aspect of biophysics. So as a result, my upcoming in that training was thinking more, what can I do, understand biological system using the physics principle. So that's where I come from. And then, of course, I need to make up all the things I did not know. So I took all the courses in cell biology, molecular biology, and genetics and the like. So that's my exposure in biology. I would say my biological background is good enough to me to be a professor in bio X and Y, but I'm not really a card-carrying biologist.
So if you had a choice and you could only do biology or physics, which would you choose to do now?
I think it would be a good idea to do the physics to start with. I think that gives you a quantitative background, analytical backgrounds, and then you pursue the biology. But I would have to say the world of biology also changing. So there could be some undergraduate program maybe more integrated, because now I encounter some of the undergraduate students at Stanford. Those guys are really sophisticated. they know enough physics, and they know enough computing, and they also know the biology. I think that are the future of integrated biology. I think the future biology I would consider to be integrative biology that would encumber what we believe for a long time, but now it manifests in a different way: physics, chemistry, and computing, mathematics, and biology.
Yeah. So on that front, reflecting on it, I guess biology is something that you do need chemistry, physics, computational, mathematics. They all come together underpinning almost all biological studies that I can think of. I'm struggling to think of an exception where you don't need at least one or two of those skills and appreciation.
I agree fully. And so now, even in my research, we initially start, of course, from a cryo-EM angle to solve the structures. But at the end of the day, after with the structure, we need to understand it. It get me into computing. It get me into really biology. So, and then I think we can think about a step further, actually, in medicine as well. So in the past, we thought, okay, we write grant, we justify because we will solve problem X and Y. But now I think it's real. I don't think it's a fantasy anymore. I think that integration of cryo-EM and cryo-electron tomography into biology and medicine is real. And of course, we need a lot of computing and AI and also physics-based to make sure what we are concluding or what we are making the models are correct, at least chemically correct. So again, we need the chemistry. I mean, one fascinating thing recently, I begin to know that, God, I need to go back to learn the organic chemistry myself. That's all the fundamental thing which I learned years ago, but never been used. But now I find very fascinating from that point of view.
I think I'd find my organic chemistry quicker to pick back up again than some of my maths or physics. I guess biochemistry's degree. So there's a lot of organic chemistry drummed in at that point. You mentioned computing and simulations. So obviously, all your work at the moment is heavily involved with cryo-electron microscopy. But you've got things like AlphaFold, which is essentially a computer you can put your sequence in and it will predict the sequence. Do you see a risk of that replacing the need for cryo-EM for structures?
Not at all. They need us even more badly than ever. Okay, and when you think about all the AlphaFold is because the knowledge that the crystallographer have been able to accumulate in the last 50 years, that provide a lot of database about what structure would look like protein X and Y, and that the AI to learn it and then predict it. But at the end of the day, it's important, particularly we talk about chemistry, we talk about the local environment, okay, and need to be precise, and it could be changed because the AlphaFold, I think I understand they can now predict more than one conformations, but exactly which one is correct. Okay, I mean, send a simulation. You can simulate using a molecular dynamic to simulate this molecule move from A to B, right? but how real it is in terms of function. Keep in mind, the purpose of our research is to understand how things work. And after we understand how things work, whether we can manipulate for better or for worse. I mean, that is the purpose.
Yeah.
That's the way I think about the purpose of research, is we understand enough, we can regulate it, we can control it, is harmful to us and other organisms. Okay. So, but I don't think AlphaFold can solve all problem. Now, I would confess AlphaFold become very convenient. If you have an unknown protein, you can predict what that is, and you can use that information and then to help you to get the ground truth. So keep in mind, our research is to get the ground truth. So AlphaFold, in most cases, would not give you the ground truth in understand its function in context.
It is an amazing bit of software, but I at York, as I mentioned earlier, my office looks out on the new cryo-EM building that's there. So certainly we're using AlphaFold, but also certainly our structural biologists are very heavily into their naturally into their cryo-EM as well. I've got to ask, you sent me some pictures, which includes, hopefully this works. So for those who are watching or listening, what the picture is actually showing, I think, an SEM on my one shoulder, but then it's a huge, well, actually, is it? It's not, is it? But you've got the large TEM, cryo-TEM as well, right. Which is really tall. I don't think you can appreciate from this picture just how big it is at this point. But what was the first microscope that you used?
Okay. My first microscope that I used was a microscope did not exist. Actually, it was made by United Kingdom company called AEI. And I couldn't remember what that abbreviation stands for. And in the old days, the British company, there's a British company make that microscope, a transmission microscope, 100 kilovolt, was a very powerful microscope. Because a lot of microscopy knowledge and foundation was laid by pioneer at both Cambridge and Oxford, as I recall, particularly in Cavendish lab, which I have the privilege to spend some months when I was a student there. So I still remember that good time. But nowadays, the picture on the right, is a very tall microscope. It's a 300 kilovolt transmission microscope. And that is what most of the high resolution cryo-EM structure being used to generate the images. And the picture on the left is a focused ion beam scanning electron microscope, which is used to micro machine a very thick cell into a thinner manner so that it can put into the tall microscope to do tomographic data. So, in the next few years, these two instruments are kind of hand in hand. One is more or less a specimen preparation. It's a very expensive specimen preparation device. The picture on my left or on your right, and then the other one is for the generated tomographic data. That is the current state of art. But there are many yet to be developed technology that I would say 5 years from now, some of these these pictures will be replaced by another pictures, bigger, more expensive, most likely, maybe even taller.
That's interesting you say that. I was going to say, because obviously I did a podcast with Richard Henderson as well, and he was raving about the 100 kV systems that Mohammed El-Gamati has certainly been doing a lot of work with.
Right.
And I'll ask your take on that in more detail after the podcast, obviously. But sometimes...
So I would be happy to comment on that if you want me to respond to Richard's hypothesis.
Oh, go on then.
Okay. So first of all, 100 kilovolt instrument is a fantastic good instrument. That's all we got started, right? So I started using the 100 kilovolt instrument to image protein crystal at 3.5 angstroms and collect electron diffraction pattern of protein crystal to 1.5 angstrom. That was done in the late 70s, early 80s. So that suggests the physics definitely allows one to get the data of atomic resolution. So what Richard suggests using 100 kilovolt is not a crazy idea. Okay, and of course he is promoting based on very strong physics base, but the evidence in the literature upon that to support his hypothesis. Okay, but I think on the other hand, the single particle, there are two types of specimen. One we call single particles, small little molecules. Like if you are interested in seeing an RNA molecule of 30 kilodaltons or 40 kilodalton, and I think that kind of instrument is well suited. Okay, so one of the excitement that Richard recently developing is to have a detector that we can collect data efficiently and effectively. I think several years ago, I don't think it is too useful because I worry about the detectors. Okay, because all the detectors are fitted to this expensive tall microscope behind you. But I think now there are a couple of companies, including Richard himself, developing detector can be able to collect images. So all these last few decades, the field hasn't really advanced because the microscopes are good, but we cannot collect the data. There are no medium to collect the data, and also the beam-induced movement. But all these technical issue has been gradually ironed out. So I would say this is probably a viable instrument. Okay. However, what I see the futures of the structural biology is cell structural biology. Okay, right now it's molecular structural biology, and definitely 100 kilovolt could do it. Like as I mentioned, small RNA, small enzymes, small proteins, particularly if a lot of drug design area, a lot of these drug target maybe 50 kD or 60 kilodaltons, and I think 100 kilovolt would definitely will be well suited. That I would agree with. But on the other hand, what I'm thinking of is looking at a bigger area of the whole cell. Now, of course, this very ambitious cell has too much stuff, too big. We can't do it. At least we can see porcelain cell. So my ambition is somewhat modest but practical, in the sense that I want to understand the organelle in the cell.
Yeah.
Okay. Now, every cell biology thought they know organelle because that's what the textbooks teach them, but I don't think we really do. So I think the excitement I would consider will be, I consider to be organelle structural biology. Okay. Now, in that case, I think we need these tall microscope, maybe even taller. Yeah. Okay. That means, because at that time point, I'm interested in atomic resolution. I always did and still do, but I'm interested in a lot of these molecules in the context of cell. So even at sub-nanometer resolution or nanometer resolution, I think I will learn a lot, particularly in the context of medicine, in pathologies, in cancer, neurodegenerative diseases, infection biology. I think there's so much, it's just around our fingertip. We can just go to make all the discovery today, next 10 years, full time. Okay. So in that sense, I say, Richard, okay, I agree with you. 100 kilovolt will be valuable, but I think at a high voltage like this 300 or even 600, maybe 1 MeV would have its play in right now or in the near future.
Yeah, I think you've intimated they're addressing different problems. They're looking at different sample types. And one of the problems, I was going to ask you actually, one of the problems with the instrument behind you is the cost. It's not easy to get, confocal microscopes have come down in price. You can have multiples of these at most universities. But the cryo-EMs is not for every university still. I think the reason I was a bit coy with the 100 kV systems, I know Richard's talks a lot with Mohammed El Gamati of York Probe Solutions. I kind of know them quite well. Mohammed was on one of my grants applications once. So I didn't want to bias it towards that direction. But I think it's a really interesting solution for enabling most universities to get something to do, some of the low-hanging fruit, some of the easier, easier sounds wrong, doesn't it? I'm going to get into trouble saying that. Some of that side of the market, the smaller molecule.
No, I agree with that. I think that will democratize some of this research activity. And the fact is, FEI have been able to sell, I was told, over 300 of this cryo, okay, the toy instrument behind you. Then the question is, I didn't expect that people would come up with that much money. I don't know where the money come from. So I think, in a sense, I'm not too concerned about the economic aspects. The fact that, the industry showed me that they're able to sell. And then my colleagues around the world capable of raising all this money. And so I'm less concerned about that. Now, think about the hospital, at least in America.
Yeah.
I mean, how equipped they are. They have a CT scan and all this. It will be cost probably as much as this cryo. There's no problem. And I can't, when Thermo Fisher in a few years ago, they said, oh, they want to make money. They want the farmer to have this kind of instrument. I said, you think too small. You need to think about every hospital in America need 1 or 2 or 3. Then you're talking my language. If you really want to make money. So I think at least I'm looking from American economy point of view. I'm not, I think it's hard to get the money. Now, for people who are interested in doing research or don't want to waste time to raise money, like what I do, I'm wasting a lot of time in managing this at the moment. I think it's a community service, the way I look at it. Is that the funding agency, the government, like the EPIC over in Diamond Light Source, and I think leads to some extent, or maybe in Edinburgh, not in Edinburgh, sorry, in Glasgow, and then like in us, in America, the NIH Center. So we set up all these centers, just like the X-ray beamline, right? In the past, nobody can afford the X-ray beamline. That really make that possible. You really revolutionize the whole field in molecular structural atomic biology, right? So I think then the problem is why people don't want to do that. Just think about the American style of living. Everybody wants to own the car, not only 1 car, 2 cars, and 3 cars. They never want to take public transportations. Why? It's a cultural thing, right? So, but other part of the world, they take bus. They walk to the bus stop and they take the bus to work and take the bus home. So I think the American scientists need to think about that way. You don't own things, you use things, and then you can, the government would pay you to use the thing freely. And I think that once you have the culture shift, then I think we'll be perfectly fine. And so like the place like EPIC and like some of the NIH Center, because not just buying the instrument, but getting the people to run it.
Yeah, the expertise.
And nowadays, all the company begin to do it. They pay people, I was told, 2, 3, 4 times more. I'm losing people. I'm actually training the people. They go to industry making more money than I do. What can I do, right? I mean, they want, that's the way it go. But on the other hand, what I can provide is I consider, I'm sure you feel the same way, our intellectual environment, something exciting. We make discovery. And we interact with people freely, and we exchange things freely, and we don't have a boss over me and you, every day, right? So that's what, that's what we are compensating with less pay. So I think, we would just have, like Richard, have even volunteered to work, without pay. We have these people, and I don't worry about it.
I was having that very discussion actually earlier on with a colleague, and we were talking about different posts and how much they get paid in different parts of the country. And if you've got Google right next to you and how much they would pay for the similar type of post. And I would say, well, so and actually academia is trying to increase the salaries to match. And And fascinating, someone, again, different conversation with someone else, said, actually, we shouldn't be trying to increase our salaries to match that. We should be paying parity salaries to the other academics that Google aren't going to poach, or whichever big company isn't going to poach. I'm not picking on Google here at all. Because actually, those who want to go into science and help, you got into it to help solve cancer. Yeah. People who are passionate about the science, it's not about the money. Yes, we have to make sure there's a good salary there, absolutely. Yeah. But at the same time, they're not going to be there because they're getting paid more than they get paid elsewhere. They're there because they're getting paid well, hopefully.
Yeah.
But they're also doing something they're passionate. It's not a job. It should never be a job in academia.
It's not a job. I'm still going to school.
So it is. It's got to be a passion, hasn't it? It's got to be a.
I agree. Yeah.
It
but definitely, like in our area, it's a very volatile because we are expensive as living in London or even more. So it's challenging. Just the cost of living is much higher. So now we are surrounded by the Silicon Valley now with Facebook and Google. I mean, it's challenging.
Yeah, but I think the best people who want to help will still be there. It's the cost of living around it that's going up so much that makes it more challenging at that point. Now I'll change subject a little bit. I'll just go back to that previous picture, which was of you mentioned public transport compared to having your own car. Well, I would argue you are public transport, because you have these instruments that are also used by many different people. And they're not owning their own cryo-EMs. We have our core facility at York, which is now a Eurobioimaging node. So people from all over Europe can come and use that infrastructure. And because they can't or don't want to afford, technology moves on so fast.
Right.
If you were to buy a car, you're going to get 5-10 years, whatever, out of it. In this case, it may last 2 years. Right. And something better comes out, and if you're not using the best, your science is no longer cutting edge.
Right, exactly.
And so you started core facilities or the structures of putting in shared labs of the EMs. When was the first time I think you did this back in Baylor, did you? Am I right there?
Right. Yeah, it's almost 40 years ago, you see, because fortunately, decades ago, NIH has a division that explicitly fund these cutting edge technologies for technologies that is not yet proven, but through that support to prove that technology to be useful. I mean, the technology, including the X-ray beam-9, the NMR, the mass spec, and then the electron microscopies. And before my time, it was the cell biology, the MEV microscope, like Keith Porter. I don't know you heard of him or not. It's a very senior cell structural biology, discovered a lot of things in the cell. And he has a 1 MEV microscope in Boulder. And the time I came in, and I was questioning, those old 1 MEV microscope would be useful or not. And some of us, including me on the committee, we thought perhaps a 300 or 400 kilovolt would be a intermediate choice, because they are, at least it can fit in the normal, well, a little bit taller ceiling, but not 2-story height. And so NIH was willing to fund me and a couple other sites to acquire those, and I was the only one that pursuing the cryo. And so and that is how I get started. So mostly developing the methodology. When I first started was the 40 angstrom through the year, from 40 angstrom to now 1.2-ish angstrom resolution. That took about three and a half decades effort. And so it's not an overnight thing in this kind of activity.
So thinking of those 3.5 decades of setting up, what's been the best time over that career?
Oh, that was a really phenomenal time, because first of all, there was no competition for 30 years. I enjoyed that. because people thought I was crazy, so they left me alone. So I could do what I want and I could do my own pace. So, one of the exciting thing was I was able to use the instrument in Berlin. I helped setting up in Berlin on the superconducting lens microscope. And I was able to get images of protein crystal to, better than 4 angstrom on images. That was exciting. And that work actually, I think, stimulated Richard to move into the imaging approaches. So I think that, to my opinion, is I was excited at that time because I went there to do the experiment myself. I helped setting it up. And that was the last instrument made by Siemens Corporation. Since then, they completely out of the business. And so that was a good one. And then at Beta, I was pushing on a 400 kilovolt microscope. So we decided at that time we want to go on single particle on viruses. And we worked with, I spent a year on sabbatical at the RMB, and then get to know a virology in Glasgow, and I get involved in working with herpes. Okay, and so Richard is always a very good friend of mine. And so I spent a year with Richard and Tony Calver and RMB. That was probably the most enjoyable year on sabbatical. That was a very memorable time in Cambridge.
I presume that was, so you sent me some pictures of you and Richard as well, which are here.
Yeah.
So I presume this was after that period though, or was that during that time? Surely this was after.
The picture I sent you was after more recent pictures, but yeah. It was, I know Richard when he first discovered the structure of bacterial dopsin with Nigel Unwin. So we were back because we were one of the very few people interested in that approach at that time, on protein crystal. So I was, was pursuing protein crystal rather than the single particles. And it was delightful that Richard came to visit me after his prize in 2017. And then the 2 other people, it happened that they were 2 senior program officers from Department of Energy in Washington visit. And so they were delighted to be with Richard as well. So that was a really good time. So Richard has been very helpful to me all this year and encouraging me to do things. And of course, I deviate from the original work doing the protein crystal by electron diffraction. I switched to the single particle. So it was not received by the community too well at that time because it was very low resolution. But I'm glad what I did. So I was improving from 40 angstrom to 20 angstrom to 10 angstrom to 9 angstrom to 6 angstrom, and eventually to 3.5 angstrom, 4 angstroms before the so-called revolution. But since I was working on bacteriophages, again, people usually don't pay attention to so-called irrelevant biological object. I wasn't working on sexy membrane protein, right? So, but anyway, but I think for technology, I think it's important to choose the right benchmark molecules so that the technology can lend itself to it. So I still very pleased what I do, but I think without that, the single particle won't, in my opinion, won't go that far. I mean, I was pushing along that period. So I think for during the period at Beta, I developed the whole thing from 40 angstrom down to 4.5 angstrom that period.
So you said quite nicely that actually the last 30 years have been your best years because you were alone. There wasn't any competition. There's competition now because it's boomed. What you've been developing is being proven. Everyone has now caught this wave and surfing it. But take away the best times. What has been the most challenging time in your career to date? I shouldn't say to date, because that sounds like you're going to get bigger challenges ahead. What's been the most challenging time in your career? Be positive on this one.
Well, I would say I have been really lucky, and I haven't encountered any time that I need to suffer one way or the other. I mean, because one of the challenging aspects is how to get people, right? So, but I foresee that problem. and I foresee it now, and I foresaw it in the past. So I prepare for it, and I will create my path to recruit people. So I welcome people, and many of the people I recruit, people might not recruit to start with. In other, I'm willing to invest on the future. So I think the challenging aspect is to find colleagues who have the same belief in the scientific destiny as I do. Now, I don't want to say yes, man, but I think I want people to have the same goal. But of course, when you do research, one should have all the degree of freedom to inquire and turn right or turn left, or completely say, this is that project, we should move on to the next one, and things like that. So I think the challenging is actually making the right decision, go and no go in some of the projects.
So you sent me some other pictures, and it's probably relevant to bring this in now. And I think this is a big graduation ceremony picture. So are you hunting around at this point thinking, who am I going to poach? Who am I going to get to come and work for us?
Well, it's challenging right now for me that when I was a beta, I know I was in the medical school. I didn't have students. The student that I want, as I point out, I prefer student with physics background. And so I create graduate program at Beta. So fortunately, my colleague was kind enough to let me do so. And I organized not within my school, but also all the neighboring institutions, because in Houston, there are multiple institutions, including Rice University, University of Houston, which they have the undergraduate, they have the basic physics and chemistry and other math and computer science departments. So I network it. We form a consortium, and that's what I leverage my environment to have recruiting students that of common interest to the biophysics or computation biology. So I was doing quite well. In fact, when you asked me about photograph, actually I come up with a photograph, which I didn't post to you, which, something like 40 plus people in the past, many of them are very successful today in holding professorship in multiple schools. So I was really looking forward to that. Now, one of my reasons to move to Stanford, I thought, that would be an environment that the students should be a premium, types of talent that I can take on. But turn out it's tougher than I think to get students at Stanford, because somehow the Stanford graduate program run in a pretty restricted way. We don't accept too many graduate students. And as a result, the supply is very limited. And I have no control whatsoever. Now, that's why I still enjoy my freedom in Texas. I say, we need more students. I just hustle for money. I can hustle it and I go to recruit, and that would be okay. But in here, it's a more traditional institution like York or Cambridge and Oxford. They have a tradition. I need to follow the tradition. And so as a result, like the picture you saw a while ago, the young students, and she's in biophysics, okay? And these students, one of my students graduated, is also in biophysics. So I was lucky to have a few students in the last 5 years, but I don't see an overwhelming group of students coming. And I also don't see many people calling over to come to work for me neither. So, I can imagine, that people may have more choices these days, number one. And number two, the cost of living in the Bay Area may be too high. And number three, they may think, oh, why still around? I thought he's retired, right? So, so the young people may want to work with younger faculty. I can understand that. But on the other hand, I'm still working 24/7. I'm okay. I survive.
So I was like, you say you work 24/7, but you must do things outside of work as well. So what are your passions? What are your hobbies outside of work?
Well,
you used to run, didn't you?
Well, I'm sorry. I really don't have anything outside my work. I literally work 24/7, even today.
But you used to be a runner.
Huh?
You used to be a runner.
Well, I know, but that is part of work, right? Part of the exercise. I need to keep myself in shape. My only period that I do think is taking a walk in the evening. But even taking a walk, I usually have my cell phone. I'm actually talking on the cell phone when I'm walking. So that's what I meant. And so my wife are not too happy with that. She keep want to take holiday and do things. So we haven't done enough of that, except that once a year we commit that you have a pictures. Yeah. So few weeks ago, I went to London and I visited Richard and others at R&B. But I also went a day in London. I have a lot of relatives. These my nieces and nephew and their kids in London. So that was fun that day. That was in London.
It's a very nice picture of, I guess, your immediate or closer family. But you also sent me a bigger
right. Yeah. So we decided that we ought to have a holiday once a year. So I have 2 daughters and I have 6 grandkids. So this year we decided something simple in Northern California. So it was in this behind you is the Pacific Ocean. So we did enjoy that week. And so that was a good thing. And in fact, several years ago, we even spent a week in London together. We also enjoyed that very much indeed. So that was my day off that week. Yeah.
And I've got to say, you're looking very dapper, very smart in this one. So what is this picture?
Okay, so that during the after the holiday, one of the grandniece got married, and so this was in the wedding. That's why we all dress up. So the ladies next to me is my granddaughter. She is a sophomore at the university in Georgetown in England, and the one in the middle is my second daughter, Andrea, and she lives in Houston. And then the lady next to her is our niece, and the far side young lady is my other granddaughter. I have 2 granddaughters, so they're all in the pictures. And in fact, this young granddaughter now, today they're in Philippines. My daughter have moved to Philippines for 3 years, so she's now in Philippines.
So I have to show this picture just in case you've missed someone and you're name dropping them all. And if I miss one out, you'd probably kill me. So the one final family photo.
Yeah, that's right.
Anyone that's missed, they've now got snow on it.
Yeah, that was one that was a farewell dinner after the wedding. The thing is just we arranged in such a way that 1 week holiday in Northern California, and then with a wedding event, and that was a brunch before we all part. And so we gathered everybody. It was another nice restaurant in Emeryville, right next to Berkeley by the bay. And there's a very nice Chinese restaurant. So we're taking a picture in front of that. So that all the 2 daughters and their 6 grandkids, their husbands, and then also my wife's sisters and nieces and their family as well. So that's one fantastic event that day. So
okay, so you were originally from Hong Kong.
Yes.
Went over to the States, stayed in the States, done lots of visiting. We might get time to have a look at where you've been visiting. But out of choice, where would you live? Hong Kong, USA?
USA.
Okay, so I'm going to go through some quick fire questions. You an early bird or night owl?
Depends on the days. I sometimes get up at 6 and then I often have a Zoom call at 7 because I still have collaborators around the group. Last night, I have a conference course at 8 p.m. because one of my former postdoc former student now is a professor in North Korea. We're working one of the really exciting paper. So that will be his morning. So we start from 8 to 9. And tonight I'm going to have a call at 9:30 p.m. with a colleague in Singapore, and because I have another colleague in Sweden, and who's an editor of a journal, and we try to put some special events in, I call computational biophysics, with my colleague in Sweden and my other younger colleagues in Singapore. So as a result, depends on the day, it could go either way, but I sleep in between.
And hasn't Zoom made things easier on that front? The one good thing about lockdowns, I think we've embraced it far more than we had before. I've got a call, I think, with someone from Singapore and Australia on Wednesday morning, a couple of days.
Yeah.
And yeah, we've all found a time zone that we could all be sensibly awake. But yeah, early morning, late evening, Singapore got off lightly, I think, on this one. So
I agree, but I actually personally did Zoom way before the pandemic. So that was part of my thing, because I actually have 2 offices at Stanford, one on campus and another at SLAC Accelerator. And right now I'm sitting in my office in the SLAC Accelerator laboratory, but I also have lab and office down on campus. So, at any one time, depends on the day. Like today, I have to go down in the afternoon on campus on a symposium for undergraduate presentation. So I'll be down on campus this afternoon. So I Zoom in between.
So I ask you, that's the early bird night owl question. Mac or PC?
Mac.
Okay, McDonald's or Burger King?
Neither.
I knew that was going to be the answer. That's easy. If you were to go to a conference, what would be the idea? They take you, you're an invited speaker, they take you out for food. What would be the best thing that they could actually serve in front of you to eat? What's your favorite food?
Well, I'm actually quite easy. As long as the food is good, it can be any food for any kinds of cooking. It could be Italian, French, American, and Spanish, and Japanese, Chinese. Okay, so the only thing I haven't yet find an exciting meal is an English dinner. I love the English breakfast, but because when I'm in Cambridge, Richard used to take me to the college, that was good, wear a gown to have dinner, and I belong a member of the care hall, so I enjoyed that fellowship. But I haven't really. I know there's some really good English pub, but I haven't really know where to go to find it. Maybe I look you up next time when I come.
Okay, so reciprocate the offer. When next time you're up in the UK, come to York, and we'll take you to a few places, so I can at least get one that will be right.
Okay, just to get train me right.
Yeah. So we'll definitely try that, and I'll make sure Lucy Collinson down in London also knows it. And the challenge is laid. Whenever you're in the UK, whoever's hosting you has to find you some good English. It does exist. It really does exist.
I know it does exist. Yeah. So, but anyway, I just need to be having some proper guidance.
Yeah. So, coffee or tea?
Coffee.
Wine or beer?
No, because I don't have this alcohol dehydrogenase enzyme in me.
So neither. Chocolate or cheese?
I don't like chocolate, but I would take cheese.
Okay. Book or TV?
Neither.
I was going to say you can't, can you? Because you're working 24/7. How are you going to read a book or watch TV? I've got to say, I've never really got into reading books because you can be reading science.
Yeah, the reason is my eyesight is no good, so I always need to modify through the Mac, right? So it's always digital. So it's but I start printing and try to look at it, but it's very stressful to my eye. And all the transatlantic flights, I always work. I never watch any movie on the long flight. I find it very productive to work on a paper or a grant proposal during the long flight. I was very productive.
Like I say, I would. I think train journeys in the UK are great for grant reviewing, grant writing, peer reviewing, so forth. I think long haul flights are a great place for a movie. It's one of the few times you actually get to stop, and I'm a captive audience, and I'm very rarely a captive audience. There's always, even at home, I'll get up and move around. There, I'm kind of stuck, so I quite like watching a movie on a plane. So you don't have a favorite film?
No, I don't watch movie. No.
Oh, well, that bang goes that question.
I'm very boring. I'm a boring guy.
Well, that's not true, because if I look at some of the other photos, you've got friends all around the world, and you have visited on sabbaticals people all over the world. So where are you in these pictures?
It was in Houston in a Robert Welch Foundation conferences, and it's a chemistry foundation. They fund research only for the Texans, and every year they host a very laborious, elaborate conferences. In that year, that was a conference that Richard turned out to be there, and Jennifer Dunner was there as well. So you asked me for pictures, and I didn't realize even I had that picture. I started looking at my cell phone. So yesterday I looked for it. I said, God, these are nice pictures. That's why I share with you.
Brilliant. So on this one, where are you here?
We were in Shanghai, believe it or not. So the one on your right is Subramaniam. Used to be NIH, now he's in British Columbia. He spent some time with Richard when he was a postdoc. And then on the right, I think is one of the rooms in Kingston, the EMDB. All right. Is the UK, the European Bioinformatics Institute, not very far from Cambridge. So we have in Shanghai we have a workshop, and that was in a restaurant. Afterward we took a picture. It's a beautiful high rise in the background, and on the right with all this scholarly, kingly looking environment, we thought about the validations of the cryo-EM structure. So I have been very active in thinking about procedure to validate the correctness of cryo-EM structures.
But you visited extensively for Saudi, Singapore, Japan, UK, Germany, I think, as well.
Yes.
Do you like traveling?
I used to like it, but now it's a hassle traveling. In my last trip to Europe, I spent 5 cities in 15 days. I never traveled like that when I fought back, but it was difficult. But I think I enjoy talking to various people. I spent some time at Oxford and at Diamond and Cambridge and London. And then also in Netherlands, I stopped by 3 different cities in Netherlands, and I visited Thermo Fisher in Czech Republic. So those are very scientifically very productive trips. So yeah, I think I learned a lot through the interactions. That's correct.
Yeah, and I think so. You're saying how you're learning as you're going on these events, but you also do a lot of not just undergraduate teaching or teaching. You also run a lot of courses as well, and you sent me some pictures of, I presume, courses based around the cryo-electron microscopy and
right.
And not just physical. So this is, I presume, at Stanford.
That's right. These pictures were events before the pandemics. And so we went 3 workshops a year before the pandemic. And so people could come in to learn. And the speakers, the top one is David DeRose, who is the grandfather of image processing. And then the one in the bottom is Jose Maria Carazo from Spain. And then with one of the JOL manager in America. So these are all taking place in Stanford, and the other were the in-person attendance. We always assume, even before the pandemic, people can log on to that. Now that's exciting, this one. These are all my European colleagues from CCP4 experts that they do modeling. So we have them the whole 3 days workshop in Stanford. I think we have more than 300 participants while they were teaching remotely. That were very successful.
Yeah, and you sent another picture with more people, but
yeah, right. Those are the audience, the snapshot.
Yeah, I just
right. But those are when you saw that these are the speakers. Many of them are from England.
So you just need to come over here and run a course. We'll do it at the Royal Microscopical Society and set one up.
I'll be happy to.
Structural cryo-EM, and we have courses, but the RMS. Actually, I noticed some of your early works, and not so even more recent ones, you published in the Journal of Microscopy as well, multiple times. And so actually, wearing my Royal Microscopical Society hat, I should just point out that some of those publications are published in there, and the authors and co-authors on it are huge names in their own rights now as well. And it's great that you supported a journal that is run by a charity for microscopy and publishing your work in there. So I thought that was, so it's just, I'm wearing another hat at that point from the RMS, but I thought that was really cool actually to see on those.
Yeah, well, we actually writing some paper. The audience are electron microscopies. We will consider that. I mean, because in the old day, that was the only journal when I was a student in those days. I think now the American microscopy and microanalysis have their own journal, but I always thought the Journal of Microscopy as a very incredible group of editors, and they were knowledgeable. So yeah, I would think about that, because the next paper we haven't decided where to submit. I mean, we're still in the drawing board, but I will keep that in mind. Thanks very much for reminding me that opportunity.
Well, if you submit that, I think Michelle Peckham, who's now chief editor, is going to owe me a drink, and that'll be that'd be very good. But it is an excellent journal.
Yeah, no, I agree.
And it's modernizing as well, and really stepping forward. The quality of publications in there have gone up markedly.
Yeah, I'd like to ask a question, if I may, because I remember I was in one of the meetings organized by the Royal Microscopy some years ago. I couldn't remember. It took place in London. I remember the event, but I couldn't remember the detail of the conference. And I often ask myself, how come the Royal Society don't put up more of these events, or some of the journal as well? Because in the old day, the Royal Society proceeding was very prestigious. I remember one of the really classic paper by Aaron Crook and others was in that journal, but I don't see that anymore. I wonder what happened to the activity in your society.
Yeah, I can answer that. So I don't know which meeting it was in particular down in London. If it was a larger one, that would have been Micro, which became Microscience, is now Microscopy. It's now MMC, Microscopy, Microscience Microscopy Congress, which is in Manchester every other year.
I see.
And actually, scientifically, that's become quite a big program now, because it brings in all the physical sciences, material sciences, alongside the life sciences. And there's generally 6 parallels, but you've got all these synergistic and life and materials together.
Right.
And people can just freely go between them. And I find it odd. I will walk into a life science session And I'll see some of my own physicists at York in the same room thinking, well, I didn't know you were interested in this area. So I learn more about them. And likewise, I'll go to the physics ones and hear what they're talking about, because the relevance and what we can learn from each other. So that's I think now beginning of July every other year.
Oh, really? Okay.
So certainly come to it. And the journal, as you say, a lot of journals started to compete, which made things thin away. But the journal's really going after quality now, and it's upping its game. It's hard. It's a very competitive market out there, and we just need to get the best publishing in what should be the best journal. I think it's our journal. It is the Microscopist journal, I would argue.
Yeah. No, I agree. Yeah. So I also work with my material science colleague at Stanford. In the last 2 years during the pandemic, we started the symposium called Stanford EMX. And so it's a 1.5 hour symposium. One talk will be given by biologists, another talk will be given by material science. So my colleague, Bob Sinclair, who used to be from a student in Cambridge years ago, but now he's a well-known professor at Stanford in material science. So he and I put together this series. It's actually Zoom, but it was really well attended because we try to integrate between the bio and non-bio electron microscopy together. So
yeah, I think it's great. I also like the fact that the exhibition at MMC has all the companies associated with both. Because again, actually the exhibition is probably the most exciting bit. I can read about the science.
Right.
Actually going around and seeing what the companies have got, and companies that I wouldn't usually see, to get ideas and new ideas. It's fantastic.
Yeah.
I realize we are over the hour mark already, and I haven't got through all your pictures, but there's one which actually I think is above your shoulder as well. This has to be one of the coolest wallpapers you can have as a Zoom background. This is all the various structures of, I think, proteins. We've got viruses, ion channels, RNA complexes. What an image.
Thank you.
And again, this is what, 35 years of work?
No, these are all this work was done within 2 years since I moved to Stanford.
I mean, 35 years of work has now come together, and now it's like a PhD, isn't it? You spend 3-4 years working, and then the last 3 months, everything pops out.
That's correct. That's right. It's
one of the coolest backgrounds. Anyway, I'm really sorry, to the hour. So actually, everyone who's listened, thank you very much for listening. Do go and see Richard's and some of the other podcasts. And Richard Henderson's is also utterly brilliant to listen to. And don't forget to subscribe to whichever various channels. But you're brilliant. And thank you so much for taking your time. I know your time is precious. You work 24/7, but it is great. And I think actually this is a great way. If you're listening to this as an undergraduate and you're wondering which lab to go to do a PhD, if you're doing a PhD and want to know where to do your postdoc, there you go. I've just done your advertising for you. Go.
I hope so.
Get in touch.
Yeah, no, I think the fun thing being a professor to have an opportunity to interact with the students, I think that's the funnest part of the job. So, because I feel the important thing is to learn from the student through their questions. That will inspire my way of thinking, how to explain better, or to discover I actually may not understand the thing I thought I understood, right? So I think the teaching and learning is very important of our life as being academicians.
Actually, I know we just finished the podcast. I've got to ask the question though before we close off. Do you find sometimes it's the naivety of the questions that is enlightening and inspires the next novel idea?
Oh, absolutely. I think, a very, very mundane questions. At the beginning, I said, oh, what a stupid question. But when you think about it, it's not that stupid, And so I'm really open to the question. I don't consider any question to be stupid questions. But so I do enjoy the interaction with either student or colleagues to have these kinds of conversations.
So I think
That was the part of the fun of the job.
that's a good note to leave it on. There really isn't ever a daft question. It could be the daft question that is the next big thing that comes out. So again, and everyone who's watching, listen, thank you very much.
Okay, thank you. I look forward to the English good dinner when I see you next.
I look forward to finding it for you.
Okay, good. All right, bye-bye.
Thank you for listening to The Microscopists, a bite-sized bio podcast sponsored by Zeiss Microscopy. To view all audio and video recordings from this series, please visit bitesizebio.com/the-microscopists.